So it's my great pleasure to introduce Peter, that will tell us about Hazelcast, and his promised there will be goodies both for the beginner in distributed computing as well as for the more advanced user. So give a big hand of applause to Peter.
Thank you. Hello, can you hear me? Yes. Okay, perfect. So, who am I? I'm working for Hazelcast as a senior developer and solution architect. In most cases, just developing. Sometimes I go to customers to help them out. I'm the author of Mastering Hazelcast 3. It will be freely available on our website. I have 13 years of Java experience, and my big love is everything related to concurrency control and distributed computing. So, Hazelcast is just the place to be. Who of you have heard of Hazelcast? Okay, it's a good number. And who is really using it? Okay. So, what is Hazelcast? Hazelcast is the leading open source Java in-memory data and compute grid. And our main goal is to simplify the development of scalable and highly available systems, as I will explain during this presentation. So why Hazelcast? It's just a 2.5 megabyte jar file. There are no other dependencies, so you never need to deal with jar conflicts. There's no need to install additional software. Often when I get on a project and get started, first few days you are completely wasting your time setting up your development environment. But with Hazelcast, it's just make a clean install and you're up and running. It's a library, it's not an application framework, yeah? So we do not determine your architecture. We can give you advice on how to create a good architecture, but you are in charge of the architecture. So it's just a jar which you include in your project. You probably will embed it within your application. There's no need to install it on different servers or something, it's just part of your application. It's free to use. There are no limitations. You can create as many clusters as you want, as many members in the cluster as you want, as much data in the cluster as you want. We provide out of the box a whole bunch of distributed data structures. They're like the atomic log and atomic reference, ID generators, logs and conditions, countdown ledgers. Most important one is the map. It's the most used data structure. You also have an executor, which I will explain during the presentation, transactional data structures. And the cool thing is with Hazelcast 3, you can even create your own distributed data structures, but I will get back to that at the end of the presentation. So, what can I do with it? Normally, if you have your application and you need to scale up, then the simple thing to do is just buy a bigger machine and you get more capacity. The problem is you cannot scale up indefinitely because eventually buying a new machine will be too expensive. So what you want to do, you want to scale out. Just add more machines to get more capacity. And the cool thing is that if you can scale out, because you have more machines, if you lose one machine, you can still be highly available because you can deal with losing a single machine. This is a demo we did at Java 1. It's a 48 node Raspberry Pi cluster. It's completely useless, but it's very nice to show. Each Raspberry Pi has 512 megabytes of memory, and it has a 700 megahertz CPU. But because there are 48 of them, and because Hazelcast is connecting all those machines together, you get quite a nice and fast environment. Now, when can you use Hazelcast? I think the most common case to use Hazelcast is just caching. That's what we see in practice. But just to call Hazelcast only a cache is really not giving it the credit it deserves because it's so much more. You can use it as a messaging solution like JMS, complex event processing, clustered scheduling. We also have a HTTP session clustering module. There are a lot of companies using Hazelcast. E-commerce companies like Apple and eBay. Apple in total has 600 members running in multiple clusters. Lots of financial organizations like JP Morgan, telcos like AT&T, even gaming companies. So there's a lot of diversity between the companies using Hazelcast. Lots of open source projects. I'm not going to repeat them all. So if you have been using these projects, then indirectly you also have been using Hazelcast. How often is Hazelcast being used? Well, this is a little bit old information. I need to update it. In October 2013, we had 3 million startups of 48,000 unique IP addresses. So where's the coder? Creating a Hazelcast cluster is very simple. Yeah, this is one line. There you have your Hazelcast cluster. So Hazelcast instance, HZ is Hazelcast, new Hazelcast instance. The cluster can be configured, of course, using XML. That's one of the ways to do it. Here you see a very basic configuration. You see some network configuration and a map being configured. If you do not specify, for example, your map in the configuration, you just make use of defaults. So if you don't specify it in your Hazelcast XML, it doesn't matter. It still can be created. Not everybody likes to use XML. We also have a programmatic API. The problem with XML is very static. And with the programmatic API, you can just generate your own configuration. You could even use the XML as a template and just modify the parts which are dynamic. So a very quick demo. Let me see. So what I'm going to do is we have a very little demo application. It's a console-based application, so I don't need to compile here. So what I'm going to do is I'm going to start 2 instances. And you will see that after a few seconds, those instances are going to recognize each other and they'll form a cluster together. Here you can see it. Yeah, on both sides you'll see members too, and now the cluster has been formed. The members they recognize each other. Everybody has seen code like this before. Yeah, it's a simple map. The problem with the map is that it isn't thread safe. So if you want to share this map between different threads, then you have a big problem. Well, I can easily fix that. Just change the type by concurrent hash map. Now its code is thread safe. But what if you want to access this product map by different threads of different JVMs? Well, then you have a problem because the concurrent hash map is an in-memory data structure. It's not a distributed one. With Hazelcast, you can very easily fix it. Yeah, just create your Hazelcast instance and get your map from the Hazelcast instance. This map is now a distributed data structure. Demo. Okay. So in this console application, we have a predefined map. It's called M. And what I'm going to do is I'm going to put a value here. Put 1 Peter. And if I do m.get 1, I'll see I get Peter back. Yeah, so the data is being shared between the different JVMs. There's a lot of things you can configure on the map. This is a really very little part of what you can do with it. In this case, I have configured the time to live. Yeah, so data which is not being used is automatically evicted from the map. You can also create indexes. If you need to do queries on your data, you don't want to do a full table scan. You can just use an index to find your data. Okay, a little bit more about scalability and high availability. So how it works internally in Hazelcast is that we chop up your memory and 271 partitions by default. It's just a user-defined number, but the default number is 271. And to determine the partition where your data lives on, we take the key, we determine the hash based on that key, and we do a mod on partition count. So this way, we can, based on the key, always find the partition where your data lives in. And each member will have a table of the mapping between the partition ID and the member that hosts it. So it's a very flexible mechanism. So imagine now that we begin with a single cluster, and just for ease of talk, we say the cluster has 3 partitions. Yeah, so this member now gets all the 3 partitions. If I start a second member, then the second member will get one of these partitions, so the data is distributed equally. If I start a third member, then every member gets a share of the load. The nice thing is that Hazelcast will automatically make a backup of your data. It depends on your configuration settings. By default, we have a single synchronous backup, but you can create up to 6. And they can be synchronous or asynchronous. With synchronous, you get more reliability. With asynchronous, you get more performance. So imagine that the third member is going to crash. Because the backup of the data of the third member is still available on member 2, we can restore data, and now we get back the original data. And also the backup is being restored on member 1. So the system is back again in a stable state, and if I want, I could even crash member 2, and the data is still there. A demo. So we are going to use the map again. I'm going to clear it first to make it a little bit simpler to understand. And what I'm going to do is I'm going to put in some dummy data. Yeah, so I just inserted 100 dummy items. So if I ask the size, then I got 100. If I ask for that particular machine, how much data do you have actually stored of those 100 items, I can ask the local size. It's 53. So if I do the same thing here, mnet size, of course it's 100. But if I do mnet local size, it's 47, because 47 and 53 is 100. The cool thing is, if I do the following, I'm going to crash this member, then since the backup is being available on the other machine, if I ask mnet size, it's still 100. If I ask mnet local size, it's also 100. So your data is highly available, and you can just add more machines to get more capacity. You can remove machines to reduce capacity. So it's a very elastic system. Okay. You also have something called the multimap. If you, in most cases, you have a single key, single value. Sometimes you want to have multiple values for a single key. Now in Java you can do that very easily with the ordinary hash map. Just use a collection as a value and you're done. The problem is if you do that in a distributed environment, if that collection, for example, contains 1000 items and it's on a different machine, you're going to download all those 1000 items, you're going to add your new item, and you're going to send back 1001 items. So to insert a single item, 2001 items go over the line. So it is not very performant. The other problem is that if you do it concurrently, it's very easy to lose data because of a lost update. Small demo. So we have a multimap here called MM, and I'm going to do a put one Peter, mm.put one Talib, and if I do a m.size, oh, sorry, I need to start up my second member. Okay, so if I do an mm.size, oh, mm.get one, I say Peter and Talib. Just like with the map, the linked blocking queue is a thread-safe data structure, just like a concurrent hash map. It isn't a distributed data structure, so it's an in-memory data structure. So if you want to share this queue by multiple threads of different JVMs, you have a problem. Now with Hazelcast you can very easily fix that. Just change to this. Yeah, you get your queue from your Hazelcast instance. What you get back is a blocking queue implementation which is distributed. So if I go back to my little cluster, we have a queue here called queue. And what I'm going to do is I'm going to offer an item. And if I do a queue.take, you will see I get the item back. But we do not provide only a normal queue, we provide a blocking queue. So what happens if I'm going to do a queue.take? Well, there's no item in the queue. And the call is going to block. Until I'm going to do this. Item 2. Now you'll see that the item, the blocked call will complete, and you get your item back on the other side. Now, like I said, we also have a JMS-like approach. With a queue, you can make a point-to-point solution, but sometimes you need to have a publish-subscribe solution. That's what we have implemented using the topic. So in the first line, I get my topic from the Hazelcast instance, and to publish a message is very simple. I just call topic.publish. To register a listener is also quite simple. Just topic at message listener, and the message listener is a very simple interface to implement. So the cool thing is, if somebody in the cluster just calls this the topic and says, "I'm going to publish this message," all machines where a listener is registered for that particular topic will be notified and will get the data from the topic. Using topics is quite easy because you don't need to install additional software. It's just embedded as a feature within Hazelcast. So if you're already using Hazelcast, using topics is very nice, and also is very performant. We also have a client solution. Yeah, sometimes you have a cluster and you want to have external members which are not participating as memory in your cluster. Yeah, so they should not contain data, they should not do all kinds of execution of tasks. You just want to have a simple client. In Hazelcast we have that. In Hazelcast 2 there were two different solutions. We merged them into a single solution. And the cool thing about Hazelcast 3 client is that it knows about your cluster layout. So it knows which members there are, and it also knows which member contains which partition. So if a client is going to ask on a map for a particular key, because it knows it can calculate the hash. Based on hash, it determines the partition ID. Based on partition ID, it determines the member, and it can immediately send the data to the correct member. It also has the load balancing policy, so in case if you have a call where it doesn't really matter on which machine is going to be executed, you can plug in a custom load balancer. And part of our enterprise extensions is also a C++ and a C# based version. We also have a Memcached based version for the people using that want to use that. Clients are very nice to use because they are quite lightweight, and you can just integrate them within your system as if it's a normal Hazelcast instance. Here you can see the client being initialized. Hazelcast instance client is Hazelcast client.new Hazelcast client. So what you get back is just a regular Hazelcast instance interface. So once you have created an instance of this class, then you don't need to care if it's a client or a full member. Okay, something about network communication. The first part, of course, when a cluster starts is that you need to discover other members in your cluster. The simplest approach for that is using multicast. With multicast, you do a broadcast on a network and you try to figure other members you try to find other members in your cluster. Multicast is very nice for local setups and development and demo purposes. Production environments never going to work. So what you want to have is a TCP IP-based cluster. And how it works is like this. You define a list of well-known members in your cluster. Yeah, so preferable 2 or 3 members in a cluster, they need to be there. And it's fine as one of them is there, but there should be a few. If a new member comes up, it's going to check one of these well-known members and see, hey, are you online? If you are online, I want to connect to you and I want to share, want to make a cluster. If all the well-known members are down, new members cannot join the cluster. So it's important that you have a few well-known members to make the TCP-based clustering reliable. We also have something else called the AVS clustering mechanism, but it's a little bit of a cheat. What we do is we look into your EC2 console, we read out all private IP addresses, we apply some filtering based on the tags you have provided and the security group, and what remains are just a bunch of IP addresses. And these IP addresses we use as well-known members in TCP IP-based clustering. So we only have 2 discovery mechanisms, and all the other discovery mechanisms can just build on top of a TCP IP-based clustering. There's a very cool open source project, JClouds, and it has support for all kinds of cloud providers. So by using JClouds, you can just read out all IP addresses within your environment and just use TCP IP-based clustering to integrate Hazelcast in any cloud. Once the discovery is done, you can just use normal TCP IP-based communication for the actual work. So, some more advanced Hazelcast. Writing a distributed application is from the beginning it looks very simple. Especially if you have a framework that makes everything look like it's local. But that's the catch. If you treat your distributed environment as a purely in-memory local setup, then you're going to create a very bad performance. So in this case, I have a log, it's called some log. I have a counter called some counter, and I have some map entries, some person. If I always need to use these 3 things together with each other, part of a process. Imagine you have an employee, and the employee has a desk, and has a car, and has a contract. And you always need to use this piece of data together for a piece of logic. Then you don't want to have this situation. Yeah, that the sum log is being stored in member 1, the sum counter is being stored in member 2, and the sum member is being stored on the sum person is being stored in member 3. Because in this case, you always need to do a lot of remoting to get your data. So it's not very efficient. And the problem here is that in Hazelcast 2, the name of your object, for example, SomLog or the some person, has two functions. First, it identifies that particular object. The second one, it also determines the partition where that object is going to live. And what we did in Hazelcast 3 is that you can use the following syntax: name at partition key. Then the whole thing is being used as an identifier, but the partition key is being used to determine the actual partition. So if I want to group the SomLog, the Som counter and the Som person within the same partition, I can use the following solution for that. Yeah, so a SomLog at foo, Som counter at foo, and Som person at foo. Because foo now is the partition key, you get the following layout. Yeah, so SomLog, Som counter, and Som person, they all fall in the partition foo. In this case, they're being stored in memory 2. Yeah, so you get all your data together. My experience is that this is the most crucial part you need to get right if you start an application, a distributed application. You need to make sure that your data is co-located and not scattered all over the system. If you fail to do that, you have a lot of remoting and you cannot really scale your system because eventually your network is going to be the bottleneck. The cool thing is you can also, sometimes you don't have the partition key at hand. In this case, foo, maybe you lost it. It's not completely visible to you what was being used. Maybe it's a UUID you generated on the fly. If you want to create a new object within the same partition key, the same partition as another object, you can just say get partition key. Yeah, so in this case it's C2 at partition key of C1. Yeah, now C1 and C2 will have the same, will fall in the same partition. We also have an executor. We extend the executor service of Java, so you will get your regular calls like execute. Yeah, this means like I have a task here, execute it anywhere within my cluster. In most cases, it's good enough. Yeah, if you get a lot of runnables, the load in most cases will be shared equally. We also have an execute task on key owner. I'm going to get back to this in the following example, but what it does is you can say this task is going to be executed on a particular partition. The other cool thing is that you can also say, I want to execute this task on one or all or subset of members. And what you can do with it is the following. So imagine you have all kinds of tasks which need to be executed, and you want to do load balancing. What you could do is every member is going to put in the hash map its load, yeah, memory usage or CPU usage, and going to publish it every 5 seconds, for example. Then, if you get a call to a process of runnable or a callable, you look up in the map which machine has the least amount of load. Yeah, you get back a member, and you just can call the execute on member. So this way you can do custom load balancing. Probably this is going to be added as a out-of-the-box feature in a future version of Hazelcast, but currently you can do your own load balancing by making use of these methods. We are also working on all kinds of different synchronization options. The ones that currently are available, of course, is the future. And the execution callback. The big problem with the future is the following. If you do a future, you get back your future, and if you do a get, the call is going to block. Blocking is horrible. First of all, you consume the thread. Second of all, blocking is dog and dog slow. So you don't want to use it if you get the chance. So the previous version of Hazelcast, it's still there and it's going to be there for a little bit, is the execution callback. What you do is you do not get back a future where you're going to do the call or the get on. You say like, if this call completes, I want this specific task to be executed. So it's much more flexible because you're not blocking. You just say at some point in time, if the answer is ready to get this task executed, and I don't care on which thread is being done. I'm currently working on something else. It's called the completable future, which is part of Java 8. Although we currently need to be Java 6 compatible, we have our own implementation, the completable future. But it provides the same functionality. And the cool thing is you can say, hey, this completable future, just like with the execution callback, as soon as the result is there, I want you to execute this particular task. And what I've seen so far, we have not merged it back to the master. You get a huge boost in performance just by not queuing. You're going to do, for example, a whole bunch of asynchronous calls to the executor, where you say, hey, execute, 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 and at some point in time you say, for example, a future that get, or you're going to do you get the callback where your runnable is being called. So you get a big boost in performance. A small demo. Let me kill this one first. I'm going to shut down one member of my cluster. And I have a bunch of predefined executors here. And they call the E1 to E16, but I'm only going to use 2. And the E is executor, the 1 or 2 or 3 is the number of threads. So what I'm going to do is the following. I'm going to execute, simulate, load 16.1. So what I'm going to do is I am going to execute 16 tasks on a single thread executor, and each task is going to take 1 second because it does a thread to sleep. So as you can see, it's very slow. Yeah, 16 tasks, a single thread will take 16 seconds. But I would like to speed this up. The simplest thing I can do is just scale up. So instead of using a single thread, I use 2 threads. Because there are 2 threads, things go twice as fast. So now I have the scale up. But I cannot create threads indefinitely on this particular machine. If it would be a CPU-bound task, I don't want to have more threads running than the actual number of cores. Because if you have too many, there will be a lot of overhead for context switching, and that's not what you want to do. So I would like to scale out. Just add more machines to get more capacity. In this case, I'm going to scale out, and I know I can cheat a little bit because I do a thread to sleep, so it's not really a CPU-bound task anyway, so I'm allowed to create more threads on my machine. So I'm going to start a second member, and I'm going to repeat the E2, the simulate load again. The cool thing is because one member has 2 threads, the other member will also get 2 threads. Therefore, I will get 4 threads. So if I do the following, you'll see that both members are doing the calculation, and in 4 seconds the stuff has been done. So I started with 16, and now I'm back to 4. And I can just keep adding machine until I get 1 second for all those 16 tasks. We have a lot of low-level synchronization primitives. There we have locks and conditions and countdown latches and semaphores. Something new in Hazelcast, we also have transactional data structures, and with this case it's the get for update. With the get for update, if you know Oracle then or MySQL, then you might know the select for update, but the record automatically is locked when you read it. Now in this case, the similar functionality is provided. We also have a map.log, and I'm going to demonstrate the map.log. It is the same as a log, only it's being stored in a map, and you can easily access it on the map. So what I'm going to do is I'm going to clear my map first, and I'm going to do. I'm going to log key 1. And if I now go do the following, m.put 1 Peter, then you'll see that the call is going to block because, sheet is not good, it's a mess because, okay, good. So I've locked key 1, and the put is going to block until the lock is being unlocked. So now I do a unlock of key 1, and you'll see that the put completed, and if I do a map.get 1, then I see Peter. I definitely need to clean up my slides. So there was a demo. Okay, this is a small race problem. Yeah, so imagine I'm going to increment the balance for a specific bank account. Yeah, so I have an increment method, the account ID and the amount. First I read out my account ID, I increment the balance, and then I put it back. The fundamental problem here is that the get and the put is not an atomic operation. Therefore, if you do it concurrently, then you could lose data, or your bank account could be too high or too low. Too high is probably good, too low is no good. So I'm going to fix this. The first approach is the following. I could use a pessimistic lock on that map entry. So here I do an account.log, and at the end, in a try-finding clause, I do a account.unlock. Always use a unlock or the locking and the unlocking with the try-finding clause, and make sure that the lock is not done within the try clause. It needs to be above the try clause. So in this case, I solved the problem by applying a pessimistic lock on the account. The problem is it isn't very performant, because there are 4 remote operations involved. I need to get the lock, and I need to release the lock. I need to get the data, I need to put it back. So 4 remote operations. So let's try to make it a little bit faster. In this case, I make it optimistic. So I'm going to do in a for loop. I'm going to ask for the account. Then I create a new account based on that old account. This is something very important, because what the Hazelcast cannot do is it cannot rely on your object reference to do the replace operation. It cannot rely on object reference to do the cas. So what we do is we do a binary content comparison. So the binary comparison of the object needs to be the same. So therefore I need to keep the old object as it was, and then I need to create a new object based on the old object. Once I create a new object, I can just say increase the balance to a given amount, and I'm going to call the account.replace. And it will succeed if the old data was still there and a new data is written. My warning is that serialization is very unpredictable, and if you, especially if you use maps, that's some of the things we saw, is you do multiple serializations and deserializations of exactly the same object, you can get different binary content. So it's tricky. Therefore, don't try to rely on serialization when using this kind of stuff, but use something else like our own APIs. So I managed to make it a little bit faster, because instead of using 4 remote operations, there are 2 remote operations. So it's a little bit faster, but still not perfect, because the fundamental problem is the following. The database is not very smart. What we do with the database is the following. We get data from a database with select statements, we modify it, and then we set it back to the database. So that's not what you want to do. What you want to do is you want to send your function to your data, and you do not want to send your data to the function, because the function often is a lot smaller than your data you're going to send. So let's try to rewrite the previous example. We're going to do that using an executor. So I'm going to create a task, the balance task, and the content of the run method is just a copy of the optimistic version we just saw. If I'm now going to call it like this, then I'm going to do the increment. I create my balance task, and now we have that method I talked about, the executing key owner. Now this runnable is going to be sent to the partition which owns that particular key, in this case the account ID, and there it's going to be executed. So now you are sending the function to your data instead of your data to your function. So that's one way of doing it. But to be very honest, I still don't like the fact that you need to do two calls to get your data in. So we can improve that. We have something new in Hazelcast 3. It's called the entry processor. And the entry processor provides roughly the same functionality as an executing key owner. So this entry processor, if you look at the process method, you see that the only thing I now need to do is entry, get value, which is my balance or my account, and dot balance plus this amount. As you see, there's no locking going on. This is due to the architecture of Hazelcast, because within a given partition, only a single thread will be active at any given moment. Because of that guarantee, you do not need to deal with concurrency control within an entry processor. So therefore, there's no locking going on here. But it's still not perfect. I would like to be even faster. Okay, this is the call for the entry processor. The accounts map has a method called executing key, where you pass in your entry processor, and so that it can be executed. But it can be faster. In Hazelcast, we have a special configuration option for a map. It's called the in-memory format. In the beginning, I found it very complicated, but after a few times, it becomes very simple. By default, when an object is being stored in a map, we need to send it over the line. has being deserialized to a bunch of bytes that goes with the line, and we can store the actual bytes on the member. But instead of storing the actual bytes, we could also deserialize the object on the other side. So instead of just storing a byte array, you have sent the object from one machine to another. Of course, it will be a copy. So if I configure that map not to be a binary in-memory format, but I configure it with an object in-memory format, then that object which is being stored there is the actual object instance. So if I'm going to get my N2 processor, it will get a reference to the object which is stored there. So there's no serialization and deserialization going on at all. Therefore, it's very fast. This is as fast as we can make it. And the in-memory format is very useful if you want to use a lot of predicates, because the predicates also need the actual object which is there. So if you use predicates and the data is stored in binary format, then for every call you need to do a lot of serialization or deserialization. But if the data is being stored in object form, the data is already in object form, you can just use it. And of course you can use it with the anti-processor. One of the new things of Hazelcast 3 is the SPI, the service provider interface. And the cool thing about the SPI is you can create your own distributed data structures. Sometimes you have special needs, and you are not happy with the data structure we provide because we cannot make everybody happy. And the cool thing is that we expose the infrastructure we use internally to create our own distributed data structures. We expose it as an API. So now you can use our API we use internally to create your own distributed data structures. For example, I was playing around with the SPI and I wanted to have a distributed access implementation. I can easily build it using the SPI. The actor is just an object living within a given partition. It has a queue, which is distributed using Hazelcast. I can send messages to it. It's all out-of-the-box functionality. The cool thing is if the actor dies, because the state is being replicated on a different member of a different machine, the partition is made alive again, the backup is being restored, and therefore the actor is being restored. So the actor can just freely move around in the cluster, it can die, but it doesn't see what's going on. It's very, very nice. We also have a very pluggable serialization API. Of course, we support serializable and externalizable. We also have a portable implementation. It's very useful if you need to connect Hazelcast with different languages like C++ or C#, because with the portable, all kinds of metadata about your objects are being sent, the fields which are there, for example, and the types of the fields. Therefore, it's also not very efficient because of all the metadata which is being sent. But we also have the binary serializable and the stream serializable of serializer. And the cool thing is you can use that to hook it up to existing serialization frameworks like Cryo or Jackson Smile or Protobuf. A little while ago I was sent to a customer and they had a very big web shop and they used Hazelcast as a cache to store all their data in memory. The problem was that they didn't have enough memory to store all their products. And Christmas was coming and it's going to be a disaster for them because they get slow response time and people go away. So the big question was, can we improve the capacity they have? Now, well, we had a few ways to improve it. The first way of improving it was changing the serialization. So we received a bunch of serialized products, and on average they were between the 10 and 20 kilobyte big. And by replacing the serialization by Cryo, on average we got a 60% reduction in size. Cryo has also an option for compression, and on average we got an 80% reduction in size. That means they could keep 5 times the amount of data in memory than with just regular Java serialization. So this is before the JVM tuning we did. Just changing the serialization resulted in a 5-time improvement of capacity. The cool thing is that the serialization is pluggable and you can override the behavior which is already there. So in this case I have a serializer config where I say for this particular class of product I'm going to use this particular serializer, in this case the product serializer. And I can create a new configuration where I register that product serializer. And the cool thing is, Hazelcast now encounters a product. It doesn't really matter if that class is serializable or externalizable. You have configured something else. So you override the behavior which is defined in the class, and you can use something you prefer to use. So in their case, we could not change the classes of the product, but this way we could just override the serialization which is going on. One of the new things in Hazelcast 3 is the MapReduce. Yeah, so if you have lots of data, you can use MapReduce to deal with all the data. We also have all kinds of enterprise extensions. Yeah, we have support contracts for if you need help. We have elastic memory. If you have very big JVMs, for example, 10 gigabytes or more, and you have a lot of data in your cache, for example, then the data typically will stay there for a long time. It will not go quickly change all the time. So what will happen is that you're going to suffer from garbage collection delays. And therefore we have a module that will store your data out of the visibility of the garbage collector. We store it off heap. And we are experimenting currently with 200 gigabyte JVMs, where the JVM itself, it thinks that it only has a few hundred megabytes of data, even though we store 200 gigabytes of data within that particular JVM. We also have a fine-grained security module and a management center. It's very convenient if you need to do profiling, because you can see what's happening in your cluster, throughput, and that kind of stuff. So it's very convenient for production environments. The future. One of the things which is on the list is topologies. Hazelcast will treat all the members in a cluster equal, no matter what the capacity is. So it could be that you have a big box with maybe 32 gigabytes of memory, and you have little boxes. Everybody gets an equal share of the load, which can be quite annoying. Therefore, currently, all machines should have roughly the same capacity to prevent things getting out of balance. With the topology, you can control, you can say, hey, this machine has a lot of memory, this machine also has a lot of memory. I'm going to call them the big memory boxes. This map is allowed to be stored on the big memory boxes. And I maybe have a bunch of very fast machines with a lot of CPU processing power. Hey, they are going to be the beefy boxes. So these executors can be run on beefy boxes. The host management center is part of Hazelcast 3.2. What we do is just host the management solution in EC2, and you can use it for free. So that's very nice to use, because you can use it for free. Dynamic creation of data structures. Currently, you need to define them up front in your configuration, but you cannot define new data structures on the fly. With dynamic creation, you can do that. One of the other very cool things is the map of maps. With the map of maps, you have more like Cassandra-like functionality. Currently, you have a single key with a single value, but sometimes you want to have a key, and then a value. And last thing is the tiered storage. Currently, all data is being kept in memory, but sometimes you want to overflow on disk. Maybe you only have 100 gigabytes of memory available in your cluster, but you have a terabyte of data available, which you want to cache, for example. Now, with tiered storage, you just overflow to disk, and all the hot data is kept in memory, and cold data is just overwritten to disk. So, are there any questions?
One question. Let us say you're putting some value in the map, and you want to put, I want to update it on a regular basis as a cache, 10 minutes interval or something. Do I need to write some programmatic implementation for that?
So you want to automatically update a particular value in a map?
Yeah, let us say for X exchange that keep on changing for a particular currency in 1 day or 10 hours or something.
You need to add custom functionality for that. We do not have out-of-the-box functionality for scheduled updating of a particular map entry. So in that case, I would...
cache eviction.
We have that. We have cache eviction in place. We have all kinds of configuration options depending on the amount of heap or the percentage of heap you want to use, that kind of stuff.
The one that you stopped one server,
yeah,
and another server got the 100 objects in it, and when you specify local size, it gave you 100, right? And then when you restart the other instance of the server, will the size get shifted? Did you get my question?
I got your question. Your question is that if the size gets shifted when new machines are being added or being removed.
Yeah.
Yes, that will happen. Hazelcast will automatically redistribute the load in a cluster. So the size will be the same because no data is of course allowed to be lost, but the actual stored data per member is going to change. For example, if you have a single member cluster, 100 items, 100 will be the local size. If you have 10 members, then plus minus 10 will be the local size.
How do we configure that shift? For example, if the data is too large and it shifts immediately, then it might contest the network, right?
So how can we configure the shift? That's a good question. What Hazelcast does is, first of all, you need to make sure that your partitions are not too big. In most cases, between 50 and 100 megabytes of data within a single partition is our recommended amount. So if you need to have many gigabytes of data, make sure you have more than enough partitions to cover that part. Once a new member is joining the cluster or members are leaving the cluster, what happens is like, okay, let's start with one. Okay, one partition is going to move. Did it go all right? Yeah, it went all right. Okay, let's get to the next partition. So it will be a 1, 1, 1, 1 until everything is being done. During that time, for that partition, there will not be any interaction possible. In the future, we are going to play with that. Yeah, like get operations, you just can continue. There's no matter. It doesn't matter if they read the partition, even though it's being moving, because you're not going to make updates anyway. The updates you need to be blocked. The problem is that you can get an out of ordering of operations we need to look carefully at. Yes.
So when you're specifying a partition key after the add sign, is there any guarantees that the key before the partition key is unique?
No. So your question is if the key before the partition key is unique. If you have multiple things in front of the partition key, so the whole thing determines uniqueness. Okay. So it's Peter at foo. That's the whole name. Peter at bar is something else than Peter at foo. Yes?
This assumes that all the machines are running the same code, right? So I mean, especially when you're running tasks on some other partition or some other member, they have to have the code there.
So your question is that if all machines need to have the same code? Yes, currently they need to do not have distributed class loading.
But then that means if you need to update your application, you have to bring the nodes down, all of them.
So you say that all the nodes need to be brought down when you upgrade your application. That's correct. That's one of the things on our radar. You want to have a rolling upgrade where you have a shadow cluster which automatically gets all the data from the old cluster. Then you can shut down a whole new cluster and a shadow cluster will take over in one go. That's something on our radar. Currently it's not there.
You talked about the eviction policies.
Yes.
Is it on access or is it the Reaper?
So I talked about eviction. I talked about different eviction policies. Yeah, there are all kinds of different policies available. Last recently used, most recent, there are a few different ones available. And I think it's all based on the get, so when a get happens.
Near cache.
Yes.
Local cache, do you have that concept also? That you have local cache that you can configure local heap instead if you have big caches. So you have the small subset of data that is hot.
Yes, we provide near caching where you can prevent that, how to call it, you need to go remote all the time with all kinds of eviction policies also on a near cache.
And controlled by the Reaper.
The Reaper?
If you have based on the eviction policy on the main cache.
Yes.
So it communicates back and forth.
Yes. Other questions?
You talked at the end about the offloading the cache onto a memory that wasn't handled by DEC. So I have kind of two questions regarding that. First question is, is that another JVM or is that implemented differently? And then the second question is at what size of memory have you seen that starts being useful to use something like that? this?
Okay, two questions. One question is, for the off-heap storage, do you use it within a single JVM or are you using a different JVM for that? It's done in in the same JVM. And we use that using unsafe. So with unsafe, the access memory, which is not part of your regular Java heap, but it's still part of your process heap. The other question...
At what size roughly have you seen benefit in using that?
Okay, so at what size is off heap going to provide more value? In most cases, what I have seen is among the 10, 12 gigabytes of data in the garbage collector is getting more and more overhead. So creating a big JVM with 40, 50 gigabytes of memory, then especially if it's sort of old data which will be there for a long time, then the garbage collector often has a pain. Okay, other questions?
Do you have the sample code available on the GitHub or somewhere?
So do we have the example code available on the GitHub?
The one which you have just...
We have the example code for the Hazelcast book freely available on the GitHub, which is 10,000 times more, contains 10,000 times more information than the little parts I just showed you on this presentation. The book will be freely available on the website, so you can use it to combine, but I'm a little bit lazy, I'm a little bit forgetful, so I often go to my book examples just to figure out, that's the way how it needs to be done.
Do you have a Scala API?
So the question is, do we have a Scala API? It's a very good question. Currently, we do not have a Scala API, but a few weeks ago, Jonas he asked us if Hazelcast could be tuned in such a way that we can support their reactive programming model they're currently looking at, and that's something I'm currently working on. So it's the computable future stuff, and it's all based on not blocking your call. So although we do not have a Scala API currently, we are making Hazelcast compatible with their whole reactive programming model. We need to have a good Scala API on top of that, but this is real fundamental core change. It's one of the biggest changes I'm currently working on is a good back pressure solution. Because if you have those asynchronous calls happening in the system, then okay. So you can, if you go to the booth, then we can talk. We can continue talking. Okay, thank you everybody. Okay.